So this was what this mouse looked like before, with the CD8 cells monitored on the x-axis and KLG1 and Y. The cells that we're interested in are right here, in the little R6 box. And you can see that after treatment, the R6 box is essentially empty. And the cells we were after, we managed to take away. So we did this in a bunch of animals. And this is the data we obtained from that. On average, these mice from this experiment had about 17.5% KLG1 positivity of the CD8 cells. And afterwards, it was roughly about 2% or so, or about a 7-fold increase again, which we saw earlier. Also of note, this does deplete normal NK cells in the way that we've done it so far. But we have hopes that since their cells have innate immunity, they may be more able to return. And if these cells take a lifetime to accumulate, we hope that as the NK cells will come back and the senescent cells or what have you won't come back very effectively. And furthermore, we have some pretty good ideas on how to just get around this problem entirely that I'm really not going to get into at this moment. But the total cost of everything we've done so far is about $30,000 in the last year. So what are we doing next? Obviously, we repeat this over a longer period of time. This was essentially we just got these cells out of the blood compartment of the mouse. These T cells are in numerous body compartments. And then they migrate between like lymphatic fluid, sequestered in lymph nodes, etc. So we need to do this over an extended period of time in order to get a significant percentage of these total senescent cells, or whatever you like to call them. After that, the obvious next step is to test the vaccine response or some other immune challenge in these mice versus mice that haven't had the treatment. And we should finally be able to test directly if all this, immunosenescence, at least according to these markers, really is relevant the way that we tend to think it has been. And of course, looking dreaming of a higher on the site in clinical trials. One thing that I would like to note is that our device is plug and play, and so if someone can think of better markers for us to go after, we can certainly do that very easily now that we have the device constructed. This is the team. Mentioned Keith, John, Tim, Brian, and Mark. I'd also like to give a special thanks to Sam's own Ben Zealand, who was the one who really got us started on using these analytic tools in a therapeutic manner. Thanks.
I've got two questions, a technical one and a broader one. Technically, have you seen if there's any leakage of either the magnetic nanoparticles or the antibodies back into the mouse?
Honestly, we haven't really tested for that. Actually, the data we just had in the last slide is only a few days old, so at this point we can't tell you.
Okay. And the more general one, mice aren't particularly good model for human immune function.
I agree absolutely.
You'll probably find half a dozen volunteers for immune studies as you're in this hall now. So when are you going to do that? Seriously, when are you going to get a demand?
In my opinion, I agree absolutely. The mice are not a good model. However, they are a good model for developing the device that we made, which was essentially our entire goal. I can't say how ready we'd be to start in monkeys or in humans, but it's obviously dependent on funding and where we do it.
That's very impressive. I'm wondering if FDA would require special
qualification of this, or is this just treated like standard blood work and wouldn't require any FDA approval?
I would imagine it would require FDA approval, but honestly, I'm not an expert on that.
There was this, sorry, can I just comment on that? There was a company doing something similar like this in the US and it went bust because it took so long to get FDA approval.
This was done in the SENS lab in Arizona. It's now moved to Sunnyvale, California.
And it was done in the last year, right?
In the last year. Well, yeah, we started about a year and a half ago.
So it correlated with your visit to our lab, right?
We started about 6 months before we started.
And you never told us that. Very interesting.
Here, there's a here on our left, there in the balcony. There was a similar study done like this. There was the process was separating the red blood cells from the white blood cells, and they were that was done on humans, and they were just using like a strong magnet, and they were taking the blood out and running through the capillaries, and there was one of them had like a large magnetic gradient and separated the red blood cells from white blood cells. It has been published in Proceeding about 2 years ago, and if you're interested, I can direct you to that study.
Yeah, let me just expand on that. In transfusion medicine, we routinely use plasmapheresis and leukapheresis, which is what you could adapt to this kind of procedure. There is an approved machine that was approved in '98, I think. It's Baxter makes it, and it's used for preparing bone marrow for bone marrow transplants and things like that. Again, it used to make feeds. I visited the lab, and I think everybody here should give these guys a big round of applause for a very nice piece of work. Okay. What is the evidence that if you remove these cells, that they will be replaced by good cells?
I don't know of any evidence, but that's what we want to find out. And I don't know of a better way of finding out.
Hi, just a quick comment. Perhaps you could hook up your fluidic work to the second pulse laser ablation.
What was the question?
More of a comment. I was thinking to hook up the fluidic work in extracting flow from the blood to the second pulse ablation topic, which was covered earlier. So you could ablate cells as they flow past.
That's one idea.
Thank you very much for the presentation. And